video, we're not going to directly start with the second course for femboy theory, but today, let's do a little exercise in abstract algebra. Of course, this exposition on math will have nothing to do with our current courses, though maybe you can apply it. Maybe in femboy theory or in position theory. So, in today's F.E.M. or F.E.M. exposition on math episode, we are going to show an exact correspondence or a clean homeomorphism between a gear algebra and a paddle wheel. But before we begin, I need to first define what a gear algebra is. So, definition, a gear algebra is a structure which I will call M, not a manifold, which is composed of some underlying set mu, M bar, and some operation, let's say asterisk. Is a structure M equipped with the morphisms psi in, psi out, and psi elevator, such that the following diagram commutes. And here's what I show why exactly we named this structure a gear algebra. So, commutes for any generators. So I'll call them sigma 1, sigma 2, sigma 3, and sigma 4. Okay. So we have our identity element, or our initial element, which I will call var theta, which maps onto generators sigma 1 and sigma 3 via the psi out function. Sigma 1 and sigma 3 map onto sigma 2 and sigma 4 respectively. And lastly, sigma 2 and sigma 4 map onto var theta. So another way of showing, so now you can see that this looks like sort of teeth of a cog. So if I were to draw a cog here, it'll be something like this. And then you can see now that the commutative diagram looks like a tooth. This is why we call it a gear. Okay. Now you can var theta here is the same thing. We only have one identity element for this unless we have multiple unless we're given a structure such as a ring, wherein we have two operations and thus we need two neutral elements. So like for example a ring, right? We have addition and multiplication. Under addition, our set forms an abelian group, while under multiplication, our set constitutes a commutative monoid. But now, if we want to construct, or what we say, when we construct a gear over a set, we call it an unfolding. We unfold a gear over a set. So now, this is one way of thinking. The reason why really we thought we need a gear is because the commutative diagram looks like a tooth of a gear. That's all there is to it. It's all aesthetically. This is all in the name of aesthetics, why we named it like that. But it has some pretty curious properties, such as, well, for one, our identity element can map onto two elements. So I guess there goes our notion of a bijective function. So psi out is not a bijective function anymore. And I don't even think you guys would call it a function because we have a one-to-many correspondence between an identity element and two pairs inside our set, which is sigma 1 and sigma 3. So okay, let me just generalize by saying that psi I psi in maps m dot m bar times m bar, so times itself, so it's Cartesian product with itself. So we have two inputs and then maps them onto just m bar. We say m bar because our identity, our neutral element, belongs inside m bar. So when we take two things from m bar, we map it onto something that's inside m bar, we say something like this. Well, of course, you guys are supposed to know that already. And then now, the elevator function, psi e, maps m bar cross m bar onto another m bar cross m bar. So it maps one pair onto another. So this E here is the thing that maps 1 and 2 to 3 and 4. This part of the commutative diagram. 2, 3, and 4. So these two arrows over here are what represents psi E. And then the thing that wraps 2 and 4 back to var theta is our psi in for the next point. So, well, let's make an example for a gear, shall we? So now that we've defined what a gear is, let's try unfolding a gear over a structure. So let's start with a simple case. Let's start with the integers equipped with the addition operation. So let's start with an abelian group. So it's easier to digest, I guess it's more universal. A non-abelian group is just a subcase of the abelian group. So if we try to unfold the gear over it, surely we'll be able to sort of unfold a gear over a non-abelian group. So long as we can unfold it over an abelian group. So example. Let Z equipped with the plus operation be an abelian group. Okay. So how do we construct a gear over, or how do we unfold the gear over Z? Okay, let's use boldface Z for this. Now, I forgot to tell you guys the notation for the gear. So if we unfold a gear over a structure, our notation is this: O dot, and then our structure, which I will call N. So O dot N. This is not a real algebra over N. Neither is it a tensor something, a tensor sum or product over N. But rather, this is us constructing a gear over N. So we're equipping N with psi in, out, and the elevator functions. So okay, so I'll just write it down here as a sort of reminder that this is equal to N psi in, psi elevator, and psi out. Okay, so let Z, boldface Z, be equal to the integers equipped with the addition operation be an abelian group. Well, one way of proving that it is an abelian group is that we take two integers and then prove that if we add them together, it would be the same as switching them. So I already proved this in a separate video in femboid theory, but it's very trivial. So you can just pick any two integers, say 1 and 2, those are integers, and then add them together, we get 3. It would be the same as 2 plus 1, which would also be 3. So that sort of gives us an intuitive proof on why the integers with the addition operation is an abelian group. Order doesn't matter. Now what isn't an abelian group, is the general linear group of order 2. So the set of all 2 by 2 matrices, of course equipped with the composition operation. So matrix composition. That would matter because applying one linear transformation and the other would not be the same as applying that last one and then the first one. So it's not commutative. And the books that say that you can commute them or you can switch the places are wrong. Okay, so let Z again. It's an abelian group, right? Abelian group. So cool. So a gear, when the first step in constructing or unfolding a gear over a structure is that we want to specify what our psi functions are. So what is our psi in, our psi out, our psi elevator, and our psi in functions. Now the best way, at least for me, or how I studied this structure, the best way to characterize these functions is via a piecewise function. Now you guys remember these things as functions that are composed of small mini functions. So what we're going to do is define psi, start with the out function, as equal to, let's say that 0 is our neutral element here. So what we're going to basically do is map 0 onto 2 elements by saying, 0 plus our first generator, let's call it small z 1. Okay? And then 0 plus small z, or actually, let's generalize it. Onto zn equal to any integer in z. So zn is inside the integers, so it's an integer. Okay? So the thing about gears is that they have to be closed under the operation we're given for the structure. Okay, then this is z sub n plus 2, such that z n plus 2 is in the integers. Okay, so that's our out function. So what we're doing is we're traveling from 0 onto the 2 elements, right? So now we're describing psi out that maps, just m bar onto m bar cross m bar. Alright, our next task is to characterize or identify, or characterize rather, what our elevator function is. Now our elevator function, if you guys recall from what I just said a while ago, is something that maps m bar cross m bar onto m bar cross m bar. Okay, so what we're doing is traveling now from these 2 integers, zn and zn plus 2, onto a new pair. And how do we do that? Well, we do that by adding these guys with their additive inverses. So under addition, our additive inverse would basically just be the minus counterpart, such that when we add them, we get 0. We get the identity element. So our psi e is equal to this piecewise function, which is zn plus minus zn, and then zn plus 2 plus minus zn plus 2 plus now, so once we add these guys, this vanishes to 0, and notice that this is commutative right here. It doesn't matter, even though the next elements here I switch it with the first element in this piecewise function, it wouldn't matter. It would work the same way. Okay, so we make them vanish off to 0, and then we add in the next pair of numbers. So zn plus 1 and zn plus 3. I'm not going to specify now where these guys come from. All of these belong in Z to preserve closeness. And notice that when we complete the operation here, it's still closed. So at the very least, groups are, gears can be thought of as groups, unless your underlying set is not a group, of course. Or unless your generating structure, we call Z here, or rather N, our generating structure. So if your generating structure is not a group, then it's certain, almost certain, that your gear is not a group. But at least it should be a monoid or a magma. It should at least have some notion of closeness in order for it to be a true mathematical structure. If it doesn't have a notion of closeness, it is just a set. Something like a coset. So now that we characterized our E, let's do the last thing in our itinerary and characterize our in function that maps m bar cross m bar onto just m bar. So we have two inputs and then we squish them into one output. Okay? I wouldn't say squish, but rather we take them to one output. So we're not reducing the dimension rather of our m. We can characterize this, or we can say that, well, m cross m bar cross m bar is just equal to m bar squared, right? This is just notational stuff, but I'd rather express it as the cross between m and itself, because we're saying, well, we have two inputs here that come from m. So m squared is a bit abstruse for new people to the subject. So I would, if I were you, just start with m cross m, because we're being specific on what we mean by it. We mean the Cartesian product of m with itself, which is an ordered pair of elements from m. Okay? So if I'm not going to diverge further, let's finish our job and characterize our in function. So let's actually specify this. Let's say this out n. This is our elevator n, and now this is our, actually n minus 1, and then this is our in for n. All right. Okay. Oh, no, sorry. This is just n, and this time this is n plus 1. So we're now heading on to the n plus 1th. We're now heading to the n plus 1th neutral element. So we specify that, 1 minute. We specify that as now what we're going to do, since we're going to map these two pairs onto the neutral element as specified by what I wrote here, what we want to do is add them by their additive inverses this time and make them vanish off the 0. We don't need to add the neutral element here. We really don't need to add the neutral element here anymore. We don't need to add 0 in. We just need to make sure they vanish to 0 for any, Zn plus 1 and Zn plus 3. So Zn plus 1 plus its additive inverse, which is minus Zn plus 1, and then Zn plus 3 plus minus Zn plus 3. And so we are done with the gear. So actually, we're not done yet. The last step here, once we're done with identifying what our psi functions are for this structure, is we equip. So we complete the construction of our gear by saying that the O dot of our boldface Z, which is our structure, or our abelian group, which is Z, is just equal to this abelian group, of course, not Z itself, but the group, Z equipped with plus, equipped with these three. Psi 0, psi E, psi in. So that completes our construction. We're done. So now, you may be asking me, okay, Professor, how about structures that have multiple operations on them, like what I said, a ring? How do we construct how do we unfold the gear over a ring, let's say, for example? Well, to construct a gear over a ring, what we have to do is specify our psi functions this time. Because since we have two operations now, we have two identity elements, and thus what we have to do is construct two separate gears. Okay? We have to construct two separate gears and then sort of express the entire gear as some union or composition of those two gears. So, okay, let's go with the real numbers this time. Equipped with the real numbers equipped with addition and multiplication operation. So these two binary operations. let's stick with the binary choice. So we have two inputs only for these things, okay? So we don't need to consider multiple elements for the time being. Okay. So now, since for this simple example of an abelian group, we considered 4 examples, but you can consider arbitrary amounts of generators in the generating set. But for a ring, let's just stick with 4 again, but this time, since we have 2 things to consider, that means we have to consider 8 generators. Okay, so EX2, consider the ring, consider the ring R plus and dot with the binary operators plus that maps R cross R onto R, and this dot operator that maps R cross R onto R. Or we can say it maps R2 onto R. But I like to, again, specify what we mean by this. Okay. Okay, so consider the ring with 2 binary operators. So we know, to show that this is a ring, you just need to show that this forms an abelian group, and this forms a commutative monoid. There are some specific rules for monoid. I already discussed a ring in FR modules, I think, F modules and F rings, I think. I already discussed what the definition for ring is, so you guys can check that out. Okay, so now let's unfold a gear over this ring. So what's the first thing we want to do? So the first thing we want to do is say that we do not have only one set of these functions. We have 2 sets now. And we need to, since we have 2 sets, we need to specify what are the functions with respect to. So we need to first construct the functions with respect to our addition operation here. So that's trivial. It's just the thing that I did a while ago. Basically add any real number R with its inverse and then all that stuff. So how about the multiplication operation? What do we do with that? Well, we know that our multiplicative our multiplicative identity is 1. So any number multiplied by 1 is just that number. So yeah, if 0 was our additive identity, now our multiplicative identity is 1. Now I'm not gonna consider a case now that R plus, right? Because I can just, okay, let's try to decompose the case. Let's try to decompose this case. So extract Z from R. So let's express R as a union now. R as a union of R without Z, without the integer. So this is a set minus. This is in a quotient group, okay? Because people in Discord, anyone who might watch this video who are advanced math students will think that this is a fucking quotient group. In fact, it is a set minus. That's it. There's a distinguishing thing. There's a difference between, let me wrap it up. There's a difference between this and this, okay? This is R mod Z. This is R minus Z. For Christ's sakes, people keep confusing that notation. How hard can it be? I mean, I get you guys are overclocked, stressed maybe, but I'm a student too. And I can tell that difference, come on. Fix your act, math students. Okay, so union of this with this. This is like saying, well, 1 is equal to 2 is equal to minus 1, 2 is equal to 1 plus minus 1, or 1 plus minus 1 plus 2. So it's like saying 2 is equal to 2 plus minus 1 plus 1. So this vanishes to 0 and then we just left with 2. So we extract something from it, actually. Yeah, pretty much. So express as a union of that, and then we unfold the gears over this thing. So now we have to consider that R doesn't have minus whole numbers and positive whole numbers. Okay? Because Z is the set of all whole numbers, basically. And also, R would not have 0. Or R minus Z wouldn't have 0. Okay, so now let's just say that this here is equipped with this, and our integers is equipped with this. So since we equipped our integers with this addition operation, we don't need to consider that case anymore. We already consider that case in example 1. So equip z with, and equip r minus z with, okay. Alright, so it's still closed. I need you guys to know that it's still closed. You know, why is it still closed? Because consider the rationals, or the rational numbers. 1/2, let's say. 1/2 is an element of R. In fact, Q is a subset of R. And since 1/2, our example, is an element of Q, it's also part of R. Okay. So Q is the rational numbers. Okay. And we didn't extract it from R. What we only extracted are the whole numbers that also are their minus counterparts. So, but the thing is, we're not equipping it with addition operations, so we actually don't need those kind of things. Like, we don't need to worry about adding or trying to make 1/2 vanish to 0. What we want to do is make it vanish to 1. And we can do that by simply raising it to the -1 exponent. Yay! So just multiply 1/2 by 1/1/2, which is just its reciprocal. 1/2 times 2/1, which is 1. Yay! Likewise, for 3/4, just multiply it by 4/3, and then we get 1. Yay! So we do have closeness, and we do have an identity element. So this still forms a group. Actually, it's a monoid, commutative monoid, because 3/4 times 4/3 is equal to 4/3 times 3/4. And there's some additional notions here. I'm not going to quite prove it. Okay. So yeah, very neat. Yay, at least it forms a group. If it's not monoid, at least it forms a group. So there is some notion of closeness here. So it's still interesting and not boring. It's not like a coset or anything. Alright, so now that we've shown that, well, it has some closeness under this multiplication operation, right? Oh shit. So sorry, I have to add 1 here. Plus 1. Because 1s are identity here, so we have to add it here. And yeah, we would still have the inverse of 1, which is 1 to the 1/1, and then it would still give us the same thing. Okay. Yeah, sorry, I had to add 1 there, so that because when we extract z, 1 gets taken with the rest, so I have to add this here. Yeah. And when we do take the union of z and then 1 is inside here, it wouldn't really matter because under the usual rules of set theory, 1 gets absorbed by its counterpart in z when we combine them. Okay, so we don't have to worry about that. Alright, so now let's specify what our psi in elevator and out functions is with respect to multiplication. With respect to addition, we will just denote them via like this. So plus parenthesis in elevator out, like this. I just sort of shortened it so I don't have to write the other size. This is just psi in elevator and out, but with the addition. So with respect to addition operation. So it's our example 1. So now for dots, basically just do dot, and then psi in now is this piecewise function. It's almost always going to be a piecewise function if you want to construct a gear over it. Okay, so let's just write out our first part here, which is z, and then psi, or rather boldface z. Yeah, plus and yeah, okay. Plus IEO. Okay, I'll just note down here. So this is our abelian group from a while ago, because z, the z that we extracted from R, forms an abelian group under addition. So okay, now let's consider our z plus 1. The inverse of -1 is still in the rational, so it's still there. So there is still closeness, even for the identity element or the neutral element. Okay, so for any q, let's say, we're technically left with only the rationals after we extract all the integers. So let's say qn. So this is in. And sorry, out. Sorry, out. First is our out function. Okay, qn plus or times 1, which is our identity, our neutral element. And I'm not going to write where q belongs in anymore. You guys already know it's part of the r minus z plus 1. q n plus 2 times 1. Okay, yeah. And then next, our psi elevator n is equal to this piecewise function, qn times qn to the minus 1, which is 1 over qn, times qn plus 1, and then sorry, that looks like a 9, so I'm going to put the thing on the bottom. Qn plus 2 times qn plus 2 to the minus 1 times qn plus 3. And then our last function, which is our dot psi in n plus 1. So that is q minus q to the n, q sub n plus 1, q sub n plus 3 times their inverses. To the minus 1, n plus 3 to the minus 1. And you can show that this is closed, alright? Show that the gear is still closed. Okay, so there. Now what we do next is just show that this R is an equipping of the union of this, guys, of this, and then this. So just show now. So I'm gonna write it here. The gear over R ring, which I'll call this just regular R. Sorry, not boldface R. Is equal to this. R minus the integers plus the singleton set 1 called union integers with these morphisms. So psi with respect to 1, IEO, and with respect to dot, psi IEO. There. Our construction is done. Whew. It's quite the thing. It's quite the thing to attach these things. So now let's go to the meat of today's video. I know it's been like 30 minutes already, and then this is like the only thing that I've discussed so far, and we're not even close to finishing the video. Okay, so what we want to do next for our next definition is we're going to construct something, a new mathematical structure called a paddle wheel, which also looks like a gear, but it's more of like a water wheel. You know those water wheels at the side of houses in like fantasy films that you capture or use the energy of water to like power some shit or something like that? Yes, we're going to construct something that looks like that. And we're going to construct that out of elements from this, or from a gear at least. So we're going to start with the simple case sigma 1 through 4, and then sub a gear. I'm not going to specify anymore what our n is here, but I will specify what generators we're going to use in this construction. So this is the most trivial one. This is our most trivial construction of a paddle wheel. The most trivial construction of a paddle wheel, which is the identity square paddle wheel, is that we just make a cylinder and then attach a unit square onto it. What's a unit square? You'll see. You guys will see. Whoops. Okay, so what's this? And still keep in mind the definition of what a gear is. So hope you guys took note about that. Okay. So let's just write it up here. Given O dot of n with the underlying set containing these generators. Of course, 1 or 0, depending on your operation. Sigma 1 dot feel too lazy to write all that. So this is our underlying set, 1 or 0, depending on what your operation. If it's plus, it's 0. If it's multiplication, it's 1. Okay, so our first step in constructing paddle wheel, or constructing the unit square, actually we don't need this in here, in this. We just need 1 and 0. Sorry, we just need 1 and 0. And 0. In constructing our trivial thing. So first, construct or have the identity interval, which is I. And this is the reason why I don't use J to denote interval. This is why I don't use I in denoting intervals. I first made this mistake when I was first getting into topology. And when we started talking about index sets and stuff like that, yeah, I had a headache trying to replace all the notations back because it was confusing, because this means the unit interval, running from 0 to 1. So this means running from 0 on to 1. In fact, we talked about this in the last footnote, or last formal footnote for F.E.M theory with curves. Okay, so we have the unit interval running from 0 to 1. So now what we want to do next is construct a unit square. So, right, you guys can think of this unit interval as something like this. So 0 onto 1, and then there's 1/2 or something like that, and all that. Now, just like how R2 is some intersection or some perpendicular sort of construction of R with itself, right? R2 space is just two-dimensional Euclidean space. What we do here, when we take the product of I with itself, is basically do the same thing. We erect another interval, another unit interval. This is 1/2, and this is 1. And so now we have a square, because notice how if I just extend this, that, and then this point here is the point 1, 1. And in fact, this square here, this area I'm shading, is our unit square. I cross I. So all pairs of points inside this square. Now notice that the point 2, 1, well, although 1 here belongs to 1/2. Although this y coordinate belongs here in this interval, 2 is beyond this interval. So this point is not inside I cross I. But 1/2, 1/2, which is precisely the center of it, is inside the unit interval, or the unit square. Okay, so this is going to be our paddle. It's a two-dimensional paddle, or it's a one-manifold, technically. It's a curve, after all. So now we have a one-manifold, a solid one-manifold, and then now, what we want to do next is we take the unit square, which is S1. We talked about this many times already, S1. S1 equals x squared plus y squared equals 1. So that the pair xy is in R2. So we take the unit square S1, unit circle S1, and then we take the product between S1 and I to construct a cylinder. In fact, this is one of the most trivial examples of constructing a tangent space at S1, or at all points of S1. So what we do is, all right, we have our circle, right? We have our S1. We assign every point here with some -1 to 1 line, and then it goes on and on like that, and then it's some beautiful, messy, but sort of symmetric looking type thing, like that. And then what we do is just fix it. We rotate these guys and make them normal to the circle, and we get something like this, which is precisely a cylinder. Because notice how, all right, I just have to enclose this region with a boundary, and there, we have a cylinder. So what we do is just make the tangent spaces, which is I here, or unit tangent spaces, or, well, let's say, okay, let's call these points psi I. Now, this has nothing to do with the psi in function. This is just psi small I. There's a distinction between, or actually, let's call it var phi, or phi I. So the tangent space of S1 at var phi I, any of these points where we have these lines on, is equal to Well, all vectors, well, let's do it with respect to the center. So we have some x value running here, or rather, we have an entirely new coordinate system here. Actually, yeah, we have an entirely new coordinate system. And we're only running along this part. So if I sort of rotate this and enlarge it into its own thing, it becomes its own coordinate system. Right, so that's like one of the perspectives or one of the important things about tangent spaces, is that you construct your own coordinate system of these things. So now, all vectors that lie within this -1 to 1 interval. So it's only running left and right, so that means our x value would stay x, and our y would stay 0. So x is inside the interval 0 and 1. Close it. So instead of all those integers that of all vectors, or tangent vectors that belong in this sort of thing. And so, right, so just a small specification or identification of what our tangent space is, or what we need to make normal to the circle in order to construct the cylinder. Okay, so now that we have our square and our cylinder, to complete the construction of the paddle wheel, what we just do is specify a point along the boundary. So our var phi I, so it's very neat that I define var I, or var phi I. And what we do is just specify or identify this thing by saying, oh yeah, okay, I'm going to have this interval be equal to one of these normal tangent spaces to S1. So that this is precisely onto here. So to finish the construction, what we would just want to do is say that I cross I, actually not I cross I, which is a component of I cross I, or I squared, is equal to the tangent space at a point var phi I of S1. And there, our construction is done. And so your finished paddle wheel would look something like this. So this is your I cross I, and this is your var phi I, and then yeah, there. So it would look like that. If you want to attach multiple paddle wheels, you need to specify it some more. So I've sort of run out of time. I suppose I'll just make a follow-up video if I can discuss more about like 3-dimensional paddle wheels, like having a definite length here. And this would actually be more sort of aesthetically accurate to a gear. So something that would be in a follow-up video or follow-up exposition. So I'm sorry if this one was quite heavy. I mean, it's literally like, yeah. But the thing is, the very odd and weird thing is that this stuff is trivial compared to the rest of abstract algebra. This thing is very simple. This is a very simple concept compared to the vast majority of abstract algebra topics. I was debating with a fellow advanced math student. Oh boy, was it quite an argument. So I'm gonna end the lecture here, and yeah, make sure to subscribe. In order to enroll into LOSC, you guys just need to subscribe and answer one of the dozens of homeworks that I posted in the course syllabus of your chosen course, of course. We're also looking for professors to teach our curriculum. We are looking for positions. If you guys want to apply as a teacher, you guys need to have at least some experience on the community, the queer community. You guys need to have, at least that's the basic requirements at least. You guys need to have at least some teaching skills. And of course, well yeah, knowledgeable is important there. You have a little bit of charisma too, I guess. So yeah, again, looking for teachers. We are looking for teachers. If you guys want to apply, do send me an email of your application, and we'll see how that goes. And also the course that you want to teach in. And note that the courses that I teach, I mean, you guys can teach in it, but only the footnotes now, because I already did the main course. Okay. So I'll probably make a revision within the day on the course syllabus on fanboy theory, and I'll probably start making the course syllabus and start studying or rather making the topics for fanboy theory 2. So yeah, see you guys in the next lecture.